Hello everyone. I've prepared this video to help you study for the final exam and highlight some important aspects of op-amps. So to fully prepare for the exam, you should become familiar with the basic op-amp configurations that we've studied. You should know how to use them and select the right one to use in a given scenario, or be able to recognize an op-amp configuration. You should be familiar with the closed loop gain, and you should be able to use circuit analysis to figure out the closed loop gain for any given op-amp circuit. To prepare, you should also become familiar with our op-amp lab, which we did in lab 3. So the basic op-amp configurations that you should be very familiar with is the inverting amplifier, the non-inverting amplifier, the summing amplifier, the differential amplifier, and all of these feature negative feedback. And then the fifth op-amp configuration is the comparator. So I'm going to go over each of those in this presentation. So let's start off with the inverting amplifier, and we see the circuit on the left and the equation which describes its operation on the right. So let's look at that equation. So we have an input voltage which is being multiplied by negative R2 over R1, so that's a scaling factor on Vn, and that produces the output voltage. Okay? And the circuit creates this operation. So when we look at the circuit, one of the things that I notice, of course, is that it has negative feedback. So that means that the output signal is connected to the negative input of the op-amp. So it has negative feedback. Okay? It's through some electrical network, which is basically R2. Another thing that I notice is that the input signal, Vn, is connected to the negative input terminal of the op-amp. And this helps me memorize that this is the op-amp with a negative gain. So now we need to know the closed loop gain, and that's just defined as AV as a symbol for it, and it's defined as V out divided by V in from that equation, from the op-amp equation, and in this case it's negative R2 over R1. So that's the closed loop gain. So now let's try and understand, what does this mean. Let's consider an example where R1 is equal to 1 kilo ohm and R2 is equal to 2 kilo ohms. Then V out, when we apply the equation, V out is going to be negative 2 kilo ohms over 1 kilo ohm, and then times V in, which works out to minus 2 V in. So we've got the equation, we know the closed loop gain is minus 2, but what does it actually mean? So let's apply it to a situation where we have some arbitrary input signal coming in, and what happens to V out. Okay, so this is just a straightforward mathematical operation, and we can just simply treat it mathematically, and all we're doing is we're inverting V in and scaling it up by 2. So what does the waveform look like? Well, it looks like this. We've inverted the waveform and scaled it up by a factor of 2. Okay? So that one is fairly straightforward, and you should be able to draw such graphs if necessary. So now, you should carefully go over your notes to understand how to calculate the op-amp equation and the closed loop gain for any arbitrary op-amp circuit that you're given. And in this presentation, I'm just going to show a very brief overview of how to do it. So when we're calculating the op-amp equation, we have to keep in mind the op-amp properties when there's negative feedback. And remember, negative feedback is when we have a connection from the output to the negative input of the op-amp. Okay? So, and when we have negative feedback, Actually, what that means is if the output voltage is going to increase, then the negative input voltage is also going to increase, okay? Or going the other direction, if the output voltage decreases, then the negative input also decreases. So then, when we have this situation of negative feedback, we have certain properties that the circuit obeys, and that is that Vn is equal to Vp, okay? And that's known as a virtual short circuit. We also know the other properties of the op-amp, which are always true, irrespective of negative feedback, is that there is no current that flows to the negative input or the positive input of the op-amp. So those are zero. And then, to calculate the closed loop gain in the op-amp equation, we use circuit analysis to find it, keeping in mind the properties of the op-amp. So then, to use circuit analysis, we could use nodal analysis. And if we define a point, a node A, over here, and we look at nodal analysis, we're looking at the currents that's flowing out of that node. And we can write our nodal equation as shown here. So now, what have we got? To the left, moving this way, we have this term here, VA minus Vin over R1. And then, moving up, we have this term VA minus Vout divided by R2. And then we have the current flowing in to the negative input terminal, and that is IN. So now, if we apply the op-amp properties, then we see that VA goes to 0 and IN goes to 0. So how does VA go to 0? Well, what we know is that VP, the positive input, is connected to ground. Okay, so that's 0 volts. Okay, so then, because we have virtual short circuit, VP is equal to Vn. So then, Vp defines the voltage at Vn, and that's 0 volts. So Va is Vn, and so we get 0 volts for Va. Okay? So then, we can go ahead and simplify the equation where we get minus V in divided by R1 minus V out divided by R2 being equal to 0. And then we just rearrange the terms to get our inverting amplifier equation. Okay, so you should be able to do this for any arbitrary circuit, op-amp circuit, and you should carefully look at your notes from lecture for more information. Okay, so our second op-amp configuration is the non-inverting amplifier, and it looks like this. So on the right we see the op-amp equation. So it's V out is equal to 1 plus RF over Ri times V in. Okay, what's interesting about this equation is that unlike the inverting amplifier where the gain is always negative, the gain in this circuit is always positive. It's always positive, and it is either 1 or greater than 1. So that's an interesting property of it. Okay, so what do we see in this op-amp circuit? So one of the things that we notice, right, is that there's negative feedback. And again, for my little memory aid, I see the input signal going in to the positive input of the op-amp, and that makes me think, yeah, the gain is going to be positive. So it's just a memory aid for me. Okay. So then, what's the closed loop gain? Okay, it's in the same format as for the inverting amplifier. So we have AV, which is our symbol for closed loop gain. Okay, and it's our V out divided by V in. So that's always the case, always how we define the closed loop gain. And then, so simply our multiplication factor is our closed loop gain from the equation, so it's 1 plus RF over RI. So, what does this mean? Well, let's use an example where we'll define Ri as 1 kilo ohm and Rf as 1 kilo ohm. And then V out is going to be 1 plus 1 kilo ohm over 1 kilo ohm times V in, and that works out to V out is equal to 2 V in. Okay, and how do we apply this circuit and what does it do? So, if we give ourselves an arbitrary waveform, then we can see how this op-amp operates on that input waveform. And all it does is it scales it by a factor of 2. So where we had, peak value of 6 becomes a peak value of 12. Okay, at 0, they both cross at 0, of course, and it's just straight math. Okay, so then let's go to our next op-amp, which is a little bit more complicated, and that's a summing amplifier. Okay, so we've seen these op-amps in our lab 3, and we did some fun stuff with the summing amplifier. Okay, so the equation for the summing amplifier is a little bit more complicated, where there's two input voltages. Okay, so there's a VA voltage and a VB voltage, and they're each scaled by RF over RA for VA and RF over RB for VB. And another important thing to note is the negative sign. So this is an inverting configuration. Okay, and hey, look, let's look at that little memory aid that I have. So both the inputs are going to the negative input terminal. Okay, so it's a way for me to memorize this op-amp configuration. Okay, so now, what about the closed loop gain? Okay, if we just break out the equation and write it a little bit more simply, like so, we just multiply out the negative sign all the way through, and I find this is actually a good way to understand the equation too. So now, when we are talking about the closed loop gain, we've got two inputs. So we talk about the closed loop gain for each individual input. So we have an AV for VA. Okay, so for the VA input. So it's just V out over the VA input, and in this case it's minus RF over RA. Okay, and we can do the same thing, the AV for VB, the VB input, and then the gain works out to minus RF over RB. Okay, so the trick is when we have two inputs, we make a closed loop gain for each of the individual inputs. Okay, so let's try to understand what the summing amplifier is doing. So if we make an example where RF is equal to 2 kilo ohms, RA is equal to 1 kilo ohm, and RB is equal to 500 ohms, then we can apply the equation. So then the equation is shown on the bottom, where we have a V out being equal to the application of the resistors to the equation, and when we simplify it, we get this equation. So V out is equal to minus 2 VA minus 4 VB. So now, what is happening here? Let's apply this to an input waveform, or sorry, two input waveforms, because we have two inputs. We have a VB input and we have a VA input. Okay, so now what we notice here is VB is a constant. It's 1 volt. Okay, and VA is a sawtooth. It's going up to 3 volts and down to minus 3 volts. Okay, so what's this going to do? So one thing that we'll notice, that our VB term here, it's minus 4 VB. So this is going to work out to be a constant term. So this is going to be minus 4 volts. So that's a constant. So it's going to be adding a constant offset to the output voltage depending on what -2 times VA is going to be. So let us see what it works out to. Okay, so now I've drawn out the circuit, and let's see what's happening. One thing here is that the -4 volts that we said that we have for this term, so that's -4 volts, that's an offset being applied to the waveform. So I've drawn this offset right here. So right now the output waveform is going to be centered around this -4 volts, okay, because that's a -4 volt offset. And then what's this -2 doing to VA? Well, it's scaling it by -2. So the minus part inverts it, and the 2 doubles the amplitude. And so we can see, by studying this, that this is the output waveform up like this. Forgive the slightly non-ideal way of drawing that waveform. So that is the output waveform. Okay. So you should be able to come up with this on your own for the exam. Okay. So you should study this and take care with it. Oops. Okay, let's go on to the next one, the differential amplifier. This is probably the most complicated one. And so we see the equation on the right, and so we have our V out being equal to R2 over R1 multiplied by the difference of V1 and V2, so V1 minus V2. And in this case, we've got a simplifying assumption, okay? We've said that R2 is equal to R4 and R3 is equal to R1, okay? So then we get this very useful relationship. So basically, we're taking the difference of two input signals and we're scaling it by some factor that is R2 over R1. Now, that mnemonic that I said about like seeing where the input signals are going to, well, we can kind of see that in this one, because like look at V2, it's going into the negative input, and we see a negative sign here, right? And then we got V1 going into the positive input, and so we have a positive here for V1. Just a little bit way of seeing what the circuit is and memorizing it. So then, what about the closed loop gain? Okay, so the closed loop gain, if we simplify the equation, we're multiplying R2 over R1 through the equation, and then we'll calculate the closed loop gain, okay, for each of the input signals. Okay, so we have an AV for the V1 input, so it's just V out divided by V1, and then we get R2 over R1 as a closed loop gain. And we can similarly find for V2 that the closed loop gain is minus R2 over R1. So then let's apply this to an example where R2 is equal to R4, that's our simplifying assumption, and that's equal to 2 kilo ohms, and then R1 is equal to R3, and that's equal to 1 kilo ohm. And then we can apply the equation, plug in the values for the resistors, and V out is going to be equal to minus 2V1 minus 2V2. Okay, so what does this mean? So if we use the same example as we did before and apply it to our new equation, to our equation for the differential amplifier, what kind of output signal are we going to get? We'll see that V1, it's a constant, okay, it's at 1 volt, and this is what it is here. So in our equation, it just gets multiplied by 2, by positive 2, so it becomes 2 volts. So it's a positive 2 volt offset, okay? And then V2 is a triangle wave. Its relation to V out is that there's an amplification factor of minus 2. Okay, so it's inverted and scaled up by 2. So let's see what that looks like. So remember, V1 is just a constant offset, and that is at 2 volts. Okay, so the waveform is going to be centered about 2 volts because our original waveform was centered at 0, and this is an offset of 2. So then we have the waveform in red, our V2, being scaled by a factor of minus 2, so the waveform becomes inverted and amplified by 2, and with that offset of 2 volts. So we get the waveform as shown here. Okay? And then I've shown you a couple of data points to help you figure out what the values are. So you can study this graph to figure out what the interpretation for these a little bit more complex op-amp circuits. So now our final op-amp configuration is that of the comparator. So what's interesting about the comparator is that there is no negative feedback, as you can see on the circuit diagram, and we have an input signal going in this case to the positive input, and we have the negative input grounded. Okay? So now the property of the comparator op-amp is that the output only goes to the supply voltages either 15 volts or minus 15 volts. Okay? And that if the positive input is higher in voltage compared to the negative input, Vn, then the output goes to the positive supply voltage. Otherwise, the output voltage goes to the negative supply voltage. So it's summarized down below, where if the positive input, Vp, is greater than Vn, the negative input, then the output voltage goes to 15 volts. And otherwise, so if Vp is less than Vn, then the output voltage goes to minus 15 volts. Okay, so what's happening in this circuit? So we've got Vn, and that's 0 volts because it's grounded. And then Vp is connected to Vin. So whenever Vin is greater than 0, this op-amp is going to be plus 15 volts. Okay, so we can see on the graph that this is the region where Vp is positive, this is the region where Vp is negative, and so on. So we can construct the op-amp output like so, where when the input signal is positive, we get plus 15 volts, like so, and if the input signal is negative, we get minus 15 volts, like so. Okay, so now this depends, of course, on what Vin is connected to, because if it was connected to some other voltage besides ground, then we would have a different output relationship. And we can have Vin being connected into the negative input terminal and then something else being connected to the positive input terminal. You just need to keep track of the properties of the op-amp and apply it correctly in the kind of circuit that you're given. I'd like to briefly touch on an important topic, and that is the concept of the saturation of the output of the op-amp with regards to its supply voltages. So in a practical op-amp circuit, we're going to have supply voltages. So let's just put supply voltages of 10 volts as a positive supply voltage and minus 10 volts as a negative supply voltage. So what's going to happen here is that our output cannot exceed the supply voltages. So we're going to have a threshold up here. Let's call that 10 volts, and a threshold down here. Let's call that minus 10 volts, where the output cannot cross that value. So let's just draw it out there like that. And so the op-amp output, which is the green line, V out, can't go above or below 10 volts or minus 10 volts. So what's going to happen is that the voltage coming down, it's going to hit the minus 10 volts and then come across and then go up again. So this part will not be experienced. The output voltage will not go below minus 10 volts. Similarly, when it's going positive, it's going to hit the positive 10 volts, come across, and then go back down again. So it'll never go above positive 10 volts. The other parts of the waveform are not affected by the supply voltages because the outputs are within the range of the supply voltages. And there's nothing magical about the values being symmetrical, like 10 volts and minus 10 volts. Okay, we can have a situation where instead of minus 10 volts we have minus 5 volts. Oops. Let's say minus 5 volts, or it could even be 0. So let's just say it's 0 volts. Okay. And then what would happen? Well, our green line would never go negative. So let's just draw what it would be, and I'll use a super thick line. So we'd never go negative. We go positive like so across, never go negative, and then go up like that. Okay, so that's if we had 0 volts as the negative voltage rail. Okay, hope that helps.